So resource page 27, everything should be filled in up to there. So if you're missing something from 2.1 to 2.6, you're yeah, is that the transformation rule page? Yeah, those are just transformation rules. 4 and 5 are just transformation rules. We're on 2.7 right now. 2.7. I wanted to talk about the quadratic. So this part is not on your quiz tomorrow, but the Vertex form is just practicing the transformation rules. So it's not going to confuse you for your quiz. This way, after the quiz, after lunch tomorrow, we can work on some practice on this. So quadratic is the vocabulary word that you're going to add. Definition, y equals x squared. I don't really have anything to add to the definition. Quadratic. Characteristics, its graph is called a parabola. I think you know that. So its vertex, that's an important word, is at 0, 0. That's kind of important. So this is resource 2.7. Everybody has their unit 2 packet so that this can get filled in and not lost. 0, 0. What does it look like? Oh, 9? I could see the owl eyes with the beak or something, but okay. Then let's write down in a table of values what x and y would equal. All right, so from -3, -2, -1, 0, 1, 2, and 3 for x. So we're going to fill in what the y values are when you square them. What happens when you square a negative number? It becomes a positive number, right? -3 times -3 is +9. -2 squared would be +4. And then 1 squared is 1. What is 0 squared? Yep. And then you'll see that it has symmetry 1, 4, and 9 again. So these are going to be points that I say a lot this year, 1, 1, 2, 4, 3, 9, when I'm talking about the quadratic. All right, so let's graph it. So you're going to graph your vertex at 0, 0, over 1 and up 1 on both sides, over 2 and up 1, 2, 3, 4. If you notice, it's symmetric, so I just do them at the same time. And then over 3 up 9. 4, 5, 6, 7, 8, 9. And then that's on both sides. So if you kind of use symmetry, what I do is why is this bouncing? Okay. If you just plot the right side of the curve, the left side of the curve is a mirror image. So when I say 1, 1, you know that that's on both sides of the vertex. 2, 4, because 2 squared is 4, that's on both sides. And then 3, 9, 3 squared is 9. And then you just connect with like a smooth curve, and we're going to put the arrows to show that it goes forever. And we're going to write down what would be the domain and range of a quadratic. Domain, all real numbers. What's my range of the parent function? Y is, can I go forever up and down? No. No. What's the lowest I can go? So y has to be greater than or equal to 0. Yep. Arrows at the top of the graph? Yes, because it goes forever. Are you good with the bottom so I can show them the top? So the two big functions this unit are absolute value, knowing that that's the V-shaped graph, where's the vertex, how to move it, and the quadratic. The other parent functions we're just identifying. This one is square root, this one is quadratic. We're not really going in depth with writing the equation or graphing those by hand. But quadratic and absolute value, you're going to have to graph some of those by hand, just like linear we did last unit. Can I move to the next page? This is just defining the parent function. A lot of graphs, yes, because when you plug in 0 to most functions, what do you get? 0. So there's an exception with like an exponential function, which we'll learn like in unit, I think it's at unit 4. What happens when you plug in 0 to an exponential function? Anything to the 0 power is 1. So it doesn't really, we don't call it a vertex. It's kind of just this important starting point, but it's not really a vertex. I don't know, do you have additional comments? It's like that way, if there was something that you wanted to write down from a homework problem or something that like you were getting confused on, you have space to add to your notes in case you want to. A vertex, so I wonder what the actual mathematical definition is. I always think of it as either the inflection point or the starting point of a curve. But see, I don't think you call on a square root graph, you don't call this the vertex of a square root graph. So I wonder if it does have to be at a point of inflection. Because a cubic function, I would say 0, 0 is an important point, but I don't call that a vertex. So I know absolute value has a vertex. Quadratic has a vertex. I wonder if it's the point of the symmetry. I'm going to Google it. Because not all, kind of the why are we even looking at quadratics? So here's a real world problem. You're going to solve several of these this unit, but this is just, they're giving you an equation and they're showing you what the graph looks like, and they're showing you why the vertex is important. So one of the definitions that you just looked up is the apex, the highest point on the graph. If you want to make the highest profit, you're looking for the vertex of the curve. So this is just kind of interpreting a graph because students tend to have a hard time with this. So it just gave you a point in your notes to go back and look at a quadratic and answer some questions. So this says, what are the x-intercepts on this graph and what do they represent in this application problem? So this represents the profit as a function of selling price of a new hairdryer model. So you're selling hair dryers, right? You might sell the hair dryer for $10. You might sell the hair dryer for $30 or $40 or $70, right? Think about how much you're willing to spend on a hair dryer, right? If you sell the hair dryer for $100, do you think anyone's going to buy it? Probably not. Well, what happens to their profit over here as the selling price gets bigger and bigger? They start to probably not sell any hair dryers and they're actually losing money, right? So where's the sweet spot? So this is saying, what are the x-intercepts on the graph? 10, 0 and 60, 0. What do they represent? What happens when I sell my hair dryer for $10? $10 though? When I sell the hair dryer for $10 on the x-axis, what happens to my profit? Do I make any money? I make 0. In the business world, that's called the break-even point. I didn't lose money, but I broke even. The school store, I think you guys are just shooting to break even, right? I mean, you're buying the stuff and selling the stuff. You think Greg Elaine School Store is like making a profit? I feel like it's covering the cost. I don't know. Anyway, so some businesses, if you're a nonprofit, right, you want to break even every year. You want to be able to help people with whatever service, like Jen's friends. They have operating costs. They're a nonprofit. They're hoping to have more money at the end of the year. But at least if you break even, like Arts in Motion, I think that's a nonprofit theater organization, right? So they're taking in ticket sales and they're just hoping to break even the cost of producing the play. So if you sell hair dryer for, here I'll zoom in. If you sell the hair dryer for what, 10 or 60, you break even. And if you want to say profit equals $0. If you own a business, you really don't want to just break even. You won't be providing for your family if you just break even, right? There's no money left for you. What's the maximum profit the company can make? And what cost should they sell the hairdryer for? So you're going to look up here at the vertex, right? The vertex is telling you all the important information up here. So what's the answer to question number 2 from the graph? What is the 35 number? What's the maximum profit? $12,500, and we want the cost of the hair dryer to be $35. So they did studies and they can sell kind of the most of them, but also make money at $35. And it says, will every quadratic graph have a maximum value? Why or why not? So this happens to be a quadratic, right? And it had a maximum value. But what about some of the other ones that we've graphed? I'm going to say no, because some of them, right, would have a minimum, right? Some have a minimum. So kind of from here till the rest of the unit, the vertex of a quadratic is going to be the answer to lots of our application problems. When you launch a projectile through the air, and I ask you either when did it reach its maximum point or what is its maximum point, I'm looking for the vertex, right? The maximum is always at the vertex. Okay, the last part I wanted to show you, now that we've introduced the quadratic, was kind of these first couple questions on just 2-9. So this is called vertex form because it's just the transformation rules. So the equation that you don't have to have memorized, but you just have to be able to recognize that this is vertex form. You don't really care that it's A, H, and K, but it's just a way mathematically that I can talk about the different parts of the equation. I want to be able to write down, what does this number do? And what does this number do? All right, so A, we call this your concavity, up or down. So basically, am I going to have a smiley face or am I going to have a frowning face quadratic? So the A is going to tell you that. And it also is going to tell you if it is stretched. I'm going to write stretched question mark because we already know what stretch means, right? If it's 2 times the number, it's stretched. If it's only a half times the number, it's less steep. So it's our concavity and our stretch. H is our left or right. So H, let's see, it goes to the left when it's a plus, right? And it goes to the right when it's minus. Maybe that'll help you remember. Inside the parentheses, remember, it's the opposite of what you think. So left is plus and right is minus. And then what does the K do outside the function? We already learned this. K moves you up or down, not concave up or down, just vertically up or down. Up with a plus K and down with a minus K. So these are going to be exactly the same as the transformation rules you already know. Flipping it upside down, stretching it right or left and up or down. So this is all just the transformation rules that you already know. And these two parent functions don't have any stretch, but we'll come back and we'll add this in another time. Like when you stretch it times 2 or stretch it times 3, what changes about our points? So someone remind me if I forget to come back and fill that in. All right, where does this graph move? What does this plus 1 do? And what does this minus 4 do? Down, yep. And what does the plus 1 do? Moves it left. See how this is just the same as what's on your quiz? So transformation rule, I move left 1 and down 4. That's where my vertex is going to go. Just like if it was an absolute value graph. Question? Can you wait like 2 minutes until this page is done? And then absolutely. Okay, so instead of drawing my absolute value graph, right, which is what you're used to doing, I'm going to draw the quadratic graph. So that's when I'm going to say the points 1, 1, 2, 4, 3, 9, and you're going to start to know what those points mean. When I go over 1 from the vertex, I go up 1 because 1 squared is 1. When I go over 2 from the vertex, I go up 1, 2, 3, 4 on each side because 2 squared is 4. And when I go over 3, how much should I go up? 3 squared is 9. So let's see. I would end at 5, wouldn't I? So I do it with symmetry across kind of this axis of symmetry here. So this is over 1, up 1. And then I did over 2, up 4. And then I did over 3, up 9. So those are the moves of the parent function quadratic. You already graphed it on that front page. All right, and then the last one for the notes, which we'll pick up tomorrow after the quiz with some practice, but at least you'll have the notes done. Can I move it down to the last one? What 2 things have happened in example 2? What does that do and what does that do? Someone's going to say it. Yep, so left 3, and what does the negative do in front of the function? So upside down, right? Or flip over the x-axis. So I'm going to go left 3. I'm going to put the dot for my vertex. And then I'm just going to make my moves downward. So over 1, down 1. Over 2, down 4, because 2 squared is 4. Over 3, down 9, because 3 squared is 9. So you're going to start to memorize those points. We're going to use them a lot. 1, 1, 2, 4, 3, 9. And I'll say it like 50 times, and you'll eventually be able to kind of just do it in your head. All right, so I'm pausing on the notes.